These studies have been replicated over and over and over for the last 30 years of attributable risk. And diet and obesity is that second huge bucket, and nobody's talking about it. Green tea is just interesting. One, because it's probably one of the better studied compounds. Two, it's widely available and it's cheap. And three, it basically has no risk. Some of that is a lot of work, but could have potential huge benefits, not just for the cancer, but for your overall health.
Jason, today I really want to go deep into cancer with you, and we're going to get into things like treatment and prevention down the line. But where I want to start is going back in the history of cancer. How far back can we go to find a documented case of cancer in humans?
I mean, honestly, it probably goes back to the beginning of humanity. We find it in ancient Egypt and all these things. There's talk, so 2,000 plus years ago, we found cases of cancer. Now, you have to understand that cancer, like a lot of diseases, is worse as you get older. So, as you go back further into prehistory, as the sort of people live only like 40 years or something like that, life expectancy in the 2,000 years ago, you're going to get a lot less cancer than you do these days. But on the other hand, there were numerous mentions of it, even in the most early papyruses that we could find. They talked about cancer, which is super interesting. So it's a disease that has been here for a long, long time.
And as we converse here, it's going to make a lot more sense that the history does go back so far. But where I want to take things next is talk about modern times and our early understanding of cancer in the 1900s and beyond. So in your book, you talk about cancer paradigm 1. When does this take place? And then what are our early thoughts when it comes to cancer and what it is and how it works?
Right. So cancer, I mean, there was sort of always this idea that cancer is a disease of sort of excessive growth. So, this is in the modern era, right? Back in the 1400s, people talked about humors and stuff, but that wasn't very scientific. So in the modern era, the sort of initial thing was that, hey, this is something that's just growing too much. And this was obvious to see, of course. You'd see a lump and then it would grow and grow and you'd see it spread. So then people were like, well, if it grows, then let's find ways to kill it. And that's the sort of first paradigm of cancer that we had. The most ancient techniques, of course, were surgical. So you just cut it out. And they did that for a long time. But it's relatively unsuccessful as it is today just to cut it out, because the whole point is that it spreads. And it's not the actual size of the tumor that kills you, it's the spread of the tumor that kills you. And as we got into the modern era, then we started to see better ways of killing cells. It's the same paradigm, but more sophisticated ways to kill cells. So instead of just being able to cut it out, then they discovered X-rays. And, X-rays were discovered in the early 1900s. And within a couple of years, people were blasting X-rays at breast cancer, for example. So it was very interesting. It was the first case, or one of the first documented cases anyway, was of this medical student who decided that, hey, he was going to just point this X-ray machine at the breast cancer that somebody had, and then luckily there was, some like a tea, a thing of tea. So he took the foil from the tea and protected the skin around it, right? And that's sort of the first X-ray therapy. So you can burn it with radiation. But that's just another way of killing cells, same as surgery. And then in the World War I, they used the mustard gases as chemical weapons. But what they had noticed with that is that it kills certain cells faster than other cells. So again, as people started to develop that, they started to develop a chemotherapy. So what you had was a paradigm, and the paradigm means the way you look at cancer, what it is. So you're still looking at it as a problem of cell growth. So therefore, a solution is killing. So you can cut it out, surgery. You can burn it with radiation, or you can poison it with chemotherapy. And it's not trivial. It's still sort of the basis of most of cancer medicine today. The problem, of course, is that there's a ton of side effects because you're killing cells. So every single one of these treatments is highly toxic to the body. And that's why you see, obviously with radiation and surgery, you can see it, but with chemotherapy, people's hair falls out, they get terrible nausea because you're killing off the lining of the intestines and stuff. But that was sort of the first paradigm of cancer, and still a very successful number of treatments developed from that. So yeah, that's where that came from.
We're going to pivot into paradigm 2 and talk about the, you know, additional understanding that scientists gained over time. But when it comes to paradigm 1, and basically all we know about cancer is there's these growths that are happening in the early days of modern times, what did they think was causing that?
They really didn't have any good idea of what was causing that. I mean, that was why we never sort of progressed. That paradigm had to shift because that was the whole thing, right? It's like they had no idea. Like you could see that this breast cancer or this colon cancer or lung cancer was getting bigger and bigger and bigger, but they didn't know why. So that led us to sort of the second great paradigm shift, which was the genetic paradigm. So we went from a growth paradigm, cell growth, to genetic paradigm. And it's not that one is wrong and one is right. They're both right. It's that the second paradigm takes your level of understanding sort of that extra level deeper. That is, instead of just saying, hey, stuff is growing, let's kill it. Again, and I'm not trying to trivialize it because it was very successful. Actually, chemotherapy and stuff did cure a lot of people. But what you're trying to do is take that to the next level and say, okay, I see that things are growing. Why are they growing? So it's not that paradigm 1 was wrong. It's just that paradigm 2, which supplants it, is an attempt to explain what is happening here. And that's the genetic paradigm. So by the 50s and 60s, as they're starting to understand about genes and chromosomes and all this sort of stuff, people started to hypothesize that, hey, we have genes that control growth, or there should be genes that control growth. At the time, they actually hadn't discovered them. Maybe the problem with cancer is that you have damage to the gene, and as you damage that gene, it starts to grow. Or you have genes, for example, that are supposed to slow down growth. And as you damage that gene, it's going to allow growth to accelerate. And by the late 70s, they in fact discovered these exact genes. So they're called oncogenes and tumor suppressor genes. So oncogenes are actually, even though it sounds like a cancer gene, it's actually a growth gene. It's a normal growth gene. When you get a mutation in the oncogene, then you get excessive expression of this growth and therefore increased growth. Tumor suppression genes, again, I love these names, but they're actually normal genes. They don't cause tumors or suppress tumors. They're normal. But the reason they're called that is that if you have a tumor suppressor gene, it's a gene that stops growth. It's a normal gene that stops growth. But when you damage that tumor suppressor gene, it allows growth to accelerate. So essentially what you have is you have a gene that basically hits the accelerator, and you have a gene that hits the brakes. So either you're hitting the accelerator or you're letting off the brakes, or both. And therefore growth is just going crazy, and that's what's causing all your problems. And then by the late 70s, of course, they discovered these exact genes. So they hypothesized, hey, there must be genes like this. And then they discovered it's super, super exciting. And so they started to develop a few treatments along those lines. So the first couple of treatments were hugely successful. So there's one called imatinib, which is for a very rare disease called CML. And it was a chromosome that got mixed up, and it produced an abnormal kinase, which is an abnormal protein. So that they did is they said, okay, now let's go fishing around for a compound that will fix this abnormal protein. And they found it, and it was a pill, and it turned this cancer that was sort of very rare but very deadly, and it basically cured it. Like the whole thing, the whole disease just basically went away in a couple of years. It was it was basically nobody had seen anything like this. It was just ridiculously good. Now this was a rare cancer, but it proved the paradigm, and the toxicity was almost zero. Why? Because you're no longer trying to kill cells, right? That's where all your side effects were coming from. You're trying to kill a bunch of cells. Now you're trying to fix the gene product, which is this kinase, so you're not killing cells. So the toxicity was so much lower. It was just an incredible drug. So this is through the 80s, 90s, and sort of 80s and 90s mostly. And then there's this other drug called Herceptin, or is a breast cancer drug, and it was even more brilliant, if anything. So on certain breast cancers, not all breast cancers, they looked for this HER2 new gene. So there's this gene that was abnormal, and it was overexpressed. So they developed a product to block it. The problem was that if you gave this very expensive drug to everybody, only a small subset of that population would be expected to benefit. So therefore, it would be very, very difficult because it's just so expensive, and a lot of people aren't going to benefit. So they actually developed the test for this gene, made it available. So now what you could do is you could test the breast cancer, and it sounds, we do this all the time now, but back then it was just mind-blowingly advanced. But you could test for the gene, see if the cancer had that gene, and then give the drug only if it had that gene. So that was the era of personalized medicine. So again, hugely successful product, a huge advance. Toxicity was low because you're only targeting those people that are going to benefit. So it was just a crazy, so this is through the 80s and 90s, there's an incredible optimism.
So you mentioned the two drugs there. And before we move forward, I'm just curious, were these the first two attempts at doing something like this and they happened to just hit grand slams? Or was this further down the road?
This was probably because you're really picking the lowest hanging fruit, right? So you're taking the ones that are falling the most into, like, you're not attempting to cure the difficult cancers. You're just trying to cure one cancer, and then you say, oh, this cancer, which is a relatively, this looks like a good candidate. So it's a low hanging fruit, and that's why it was so successful, because you're picking the easiest one to do, and then you hit the grand slam, but only for that one, right? If you have a different kind of cancer, it's you're sort of out of luck. But on the other hand, for those people that had it, so it's sort of a combination. One, they were grand slams, but it's probably because you took the easiest ones to hit, right? You took the softballs that were lobbed at you rather than the hard ones. So
Okay, well, let's continue the story beyond that then. So they hit these couple of grand slams with the easiest quote unquote types of cancer to treat that way. What happened when they kept pushing the envelope and getting into the more tricky ones?
yeah, so that was so people were blown away. Like, it was just, people were like, this is incredible. And it really was. So this is through the 90s. People were like, okay, so this is how you're going to cure cancer. We have this new paradigm, which is that the genetic paradigm. It's the genes that are controlling the growth. So whenever you're treating a disease, you got to get back to the root cause of the disease, which is the sort of not the growth, but the genes, because this new paradigm was much more advanced. The idea at the time was that what you're going to do now is simply take one cancer, say colon cancer, you're going to look for the genes and then fix those genes, and then you've cured cancer, right? So you're looking for one or two genetic mutations of each cancer, and then fix it, and then figure out a way to fix it. But hey, that's not that hard. Once you really focus on the problem, then you can find a thing. So this sort of coincided with the sort of Human Genome Project, which was the idea that we could map all the genes of a human being. And this was 2000, sort of finished around 2000. It was very hard to do at the time because it was very expensive. It was all new technology. I mean, nowadays I could sequence your genes for like, $150 in 2 days, right? I could take anybody and sequence their genes for like ridiculously cheap. But this was a multinational sort of thing. It took millions of dollars to do one single person. But that was the 2000s. And they said that this is great. So this is going to basically figure out all the genes of a single human being, We're going to look for these growth genes. We're going to fix them. So it came and went, and as it went on, it turned out that there was very, very few genes for sort of few products that were going to work as well as those first initial sort of grand slams. And they looked for the genetic defects of cancer. And what happened was that as they started to look, by the mid 2000s, they started to realize that there's not just a few mutations in cancer, there's like hundreds of mutations. So if you take a person with colon cancer, for example, it's not the one gene that's defective or two genes that are defective. You would have like 70 genes that are defective, right? Or mutated. So the problem is that it was all different in different people. So if you had one person in your cancer clinic with a type of colon cancer, so person A had 70 distinct genetic mutations. Person B with the exact same looking colon cancer had 70, but totally different than person A. It was ridiculous. So when they cataloged all the mutations of cancer, because they've done this, you're looking at the total number of mutations in cancer somewhere around 7 million. That's probably an underestimate. There's probably like 18 million genetic mutations in cancer. So it's not one mutation, one cancer, right? One cancer, 70 mutations. Well, you can't give 70 drugs to one person and then give 70 drugs to the next person. It's just an impossible task. And that's why the genetic paradigm ultimately sort of floundered a little bit, because it didn't it didn't develop the drugs that we needed. So it made very little difference in terms of actual helping, because there's these two initial ones, but even now in 2022, you look at these genetic treatments of cancer and you look at how many of these drugs have actually been developed that have made a huge difference, right? And it's probably about 5, 7 maybe drugs that have really made a big difference, and none that made the sort of earth-shattering impact of the sort of initial two. So the genetic paradigm was, it is correct, of course, but there was more to it than that, right? Because again, it's not that there weren't genetic mutations. There were. It's just that there was so many genetic mutations. So then, you sort of ran into a wall. And this is where we were in about 2010, 2011. We are 20 years into this genetic paradigm. Every drug company on earth was looking for genetic drugs that follow this genetic paradigm, and nobody could find any because there's just too many. Like, you can't target that number of genetic mutations. It's like if you're overrun with ants and all you have is like a bazooka. It's like, well, you can kill one ant with your bazooka, but there's like 10,000 more, right? So you're just getting swarmed by these mutations that you can't treat because you can't design that many drugs. So that was sort of the low point after the genetic mutation, and then realizing that, hey, there has to be something further, because again, what is driving these genetic mutations?
So one scientist started to realize, we're heading down this rabbit hole and we can see that it's not going to have the outcome that we initially envisioned. What was the pivot from there, and when specifically did that happen?
So this is where it gets interesting, and the story takes us to about the early 2010s, I think. And this is now the pivot to the evolutionary paradigm of cancer, which most people don't even realize we're in. So the genetic paradigm had clearly failed, but most people, like, 100% of medical research in cancer was focused on the genetic paradigm, looking for more genes. It's like, you have 6 million of these. Why are you looking for more? Right? It didn't make any sense. But in the sort of early 2010s, the National Cancer Institute started to think, okay, this is not going nowhere. So we're going to start to ask other people to weigh in on this cancer problem. So they asked Paul Davies, who is an astrophysicist. And he said to them, what? I know nothing about cancer. And they said, good. because then you can give us some fresh insights into cancer, which is very, very perceptive of them, actually. It was very, very interesting. So anyway, he started to look at cancer, and he started to think about cancer, and he started to say, okay, well, there's a couple of issues here. One, why is cancer doing this, right? So we know that there are genetic mutations that are causing growth. But what is ultimately driving these cells to mutate in this way? The genetic paradigm, of course, said these were random. And that's ridiculous. That's a crazy thought. And it's one of the key reasons why the genetic paradigm fell apart, and it's called the somatic mutation theory. But it says that these are essentially random mutations. Because if you take smoking, for example, smoking is it's a well-known thing that causes lung cancer. But what they're saying is that the smoke mutates genes, but it's not targeted. It's not a targeted therapy. So why is it affecting the growth gene? They're saying what people said was that, well, it's a random mutation. It's just that you're taking so many sort of shots on net that eventually one of them will hit this critical piece. So if you're not taking all those shots on net because you're not smoking, then you're not going to hit the growth gene. Maybe you're unlucky and you get it, but if you're taking, if all this smoke is causing all this damage, which is causing all these mutations, you're taking thousands of shots on net every year, so therefore you're going to affect this one. The problem is that cancer is not random. That is, if you look at one person with lung cancer and a second person with lung cancer, those cancers behave almost identically. They look the same. So how can you say, so of the millions of people that develop lung cancer, all of them look the same? You classify them and they're like stage 1, stage 2, stage 3, stage 4, but they all look the same. They all behave the same. They all have the same physiology. If it's truly random, how can that happen? Right? It's like saying to you and me, okay, paint a picture. Paint whatever picture you want. And you and I paint the exact same picture. And then you say, oh, it's just random. And then millions of people with no instructions other than paint a picture, paint the exact same picture. It's not random. It's not random in any sense. You can take a person with colorectal cancer in 2022 in America, male, white, and you can take a colorectal cancer from 100 years ago on the other side of the earth, a Japanese woman, different sex, different nationality, half a world away, and those two cancers will look the same, even though they have completely different mutations. How does that work? How can you say that's a random occurrence? Right? So that was one of the big problems, is that this idea that this is a random mutation, it doesn't fit. And then he started to think about, why does every cell have cancer, right? So if cancer is sort of this random mutation, why does every cell in the body, why does it all have the potential to be cancerous? And not just that, but if you look, there's cancers in every animal, right? Dogs get cancer, cats get cancers, rabbits get cancer. In fact, even the most primitive multi-celled organism, which is called a hydra, one of those things in high school where you put a drop of water and you look inside, you see a hydra, very, very primitive. They found cancers even in hydra. So again, this is not a disease of humanity. So if you're looking for the answer of how cancer develops in humans, you're looking at the wrong thing, because it actually goes way past, way, way, way beyond, right? Hydra were there sort of millions of years before we were there. We didn't develop. These are primitive, they're multi-celled organisms, but they're very primitive, and they still get cancer. So if you're looking at tobacco smoke or something, you may not find it, because you can get cancer anywhere. So that was one of the things I said. So if you're going to look for it, you're going to have to look way back in evolutionary time, because it's not found in sort of the modern human. Yes, it's more common in modern humans because we're bigger, we live longer, that kind of thing. But why cancer develops is not there. And his idea was that it's actually an evolutionary disease. This is a problem that developed as we went from being multi-celled or single-celled organisms to multi-celled organisms. Um, and it's a bit of a complicated story, but that original change from single cells to multiple cells is where cancer sort of originated, because there's a difference in sort of single-celled organisms versus multi-celled organisms. Because if you're a single cell, you're going to want to compete against your other cells, whereas if you're multi-celled organisms, all those have to cooperate. So the single cell has a different sort of priority. It's a survival mandate, right? You got to survive, you got to reproduce, you got to grab resources for yourself, you got to grow, you got to move around to find new environments. And he said, well, hey, that's exactly what cancer is, right? It's behaving like a single celled organism. The whole problem is that this, you know, breast cell, which was part of a multi-celled organism, now has somehow decided that it's going to act like a single-celled organism. It's going to try to sort of grow. It's going to try and grab resources from around it, right? So if you think about it, the breast cancer cell will invade into the liver to grab all its resources. That doesn't happen in a normal cell. The breast cancer cell is going to move around the body, try and spread itself as far as you can. That doesn't happen in a normal breast cell. But these are things that single-celled organisms do. And so the idea of this evolutionary paradigm is that all cells in our body and all cells of multi-celled animals, because we originated from single cells, we have this sort of original blueprint of how to act. And it's a sort of survival, this toolkit, if you will. And this original sort of blueprint never got erased. But as we evolved into multiple celled organisms, what we did was we took this original sort of survival blueprint, these genes that said, hey, grow at all costs, spread yourself around, grab resources from other people, right? This original sort of survivalist toolkit, we never got rid of it. That's not how evolution works. But what we did was we added pieces onto it. We added pieces to say, stop growing, stop moving around, stop trying to, invade other places. So we added all these things to sort of suppress that original sort of intention of the cell to try and compete against its neighbors. And it's sort of like if you take a wild bear and you train it to dance, right? It's still a bear. If you get it mad, it's still going to kill you, but you've suppressed all its natural tendencies. So all the cells in our body have this sort of original blueprint, and that's why every cell behaves like that. So every cell can turn cancerous. In fact, every multiple celled organism can get cancer, and that explains perfectly why that sort of conundrum. It also explains why cancers are not random. That is, if you have every single cell in the body has this original survivalist blueprint, we've added all these extra pieces around it to sort of suppress the original sort of intent. But as you knock off these other pieces, what shines through is this original survivalist blueprint. And it's going to be the same no matter if you're in 2022 or if you're in 1600 BC, right? It's the same original thing. That's why those cancers look the same, because we all had that same original blueprint. Sort of like if we all had the same picture, which is just under wraps, and all we did was we went, hey, and unwrapped it. It's the same picture, right? But it existed there originally. And that's why they look the same, because your picture, my picture, were both there. We just unraveled it or opened it, and there it was, right? As opposed to us painting it, right? Which makes no sense. So that's the idea, is that this original, the way that we evolved, and this is sort of the evolutionary paradigm, the way that we evolved, that kernel of cancer, that original survivalist blueprint exists in every single cell of every single animal that has ever existed. Most of the time, we have all this stuff to keep all that suppressed. Just like if you have a wild bear, you keep it happy and everything's fine, right? You keep it suppressed and it's fine. As you get older, you're going to sustain damage And the damage is going to knock off one of these pieces that lets it shine through. And things like tobacco smoke, for example, is a source of damage to the cells. So is aging. Aging, you're going to get damage, right? So when you're young, you have all these pieces that keep that original cancer under wraps. Well, over time, it gets knocked off. And then the other thing that's it tells you, so this is the evolutionary paradigm. What it's saying is that the cell is actually evolving to become its sort of more original survivalist blueprint, but that our body we actually have cancer cells all the time because they're developing all the time because we knew that we have this sort of original sort of survivalist imprint, right? It's like the wild bear. You know that it's still a wild bear, so you still keep an eye on it. It's not like you just let it go. So our body has actual cells, the immune system, that actually fight this. So if you think about the breast cancer cell as something that evolves into sort of a more, in fact, it's not forward evolution, it's sort of a backwards evolution. So it's called atavism. If what's happening is that you're knocking off all this blueprints, you're allowing the original sort of playbook to sort of emerge, well, that's happening all the time. So therefore, our body has developed defenses against it, and those are the immune system. So when you develop this sort of original, you've actually turned almost into a new species, and that's how our body sees it. It's like a new invasive species that it has to fight. So anything, and this is happening all the time. It's happening in you, it's happening in me, it's happening in everybody. But your own immune system is going to find these sort of people and target it, just like, a policeman, right? It's like you have a city and you have policemen because if you have criminals, you go and catch them, right? Same thing here. As soon as you start to see this new species developing, that's sort of the original sort of single cell instead of it's behaving like a single cell. Your body is like, oh, okay, we need to get rid of it because it's going to be a problem. So it sends it in and gets rid of it. And then it's really as if you stress the system. So if you suppress the immune system, you're going to get cancer. So every single drug that suppresses the immune system raises the risk of cancer. But anything that's causing damage to cells, right? You have this original cancer playbook, you have all this stuff here. Anything that causes chronic damage to cells is going to cause this damage and allow this sort of kernel of cancer to shine through. So whether it's tobacco smoke, which is chronic inflammatory damage, or it could be radiation, chronic low-level radiation can do it, like we used to see in in the radium, the exposure to radiation early before we realized it caused cancer. Asbestos, for example, caused chronic inflammation. Any chronic inflammatory disease like hepatitis B, hepatitis C, they would cause cancer. Anything that causes the immune system. So this evolutionary paradigm says that, hey, the problem is this. We have cells that were originally going to behave like single-celled organisms. In evolutionary time, we've created things to suppress that, and as you knock off the things that are suppressing it, it's allowed to go through. So they've actually looked now at the study of the genes that cause cancer. And what's very interesting is instead of just saying, oh, what are the genes? They went back and they said, let's look at these genes that are mutated during cancer, and let's look at the evolutionary age of them. And all of them are concentrated just at that transition from single cell to multiple celled organisms. It's very, very striking. So all of those mutations are there. All of the more recent genes that we have, it doesn't matter if you mutate them or not. It makes no difference. It's those genes that are sort of suppressing that original single cell tendency. All the more recent genes, you mutate them, it doesn't matter. But you mutate those genes that are taking care of that problem, then you do get cancer. So the idea is that it's really a reaction to a chronic damage. Any kind of chronic damage can cause cancer. And if you think back as to what causes cancer, because people think, oh, we don't know what causes cancer. No, we know a lot about what causes cancer. Smoking causes cancer. Asbestos causes cancer, soot causes cancer, all kinds of things cause cancer, but all of them cause chronic damage to our bodies. And that's again, it's not saying that the genetic paradigm was wrong, but it's trying to answer, it's trying to go that next step and say, why are all these genes mutating, right? Just like the genetic paradigm said, why are all these cells growing? Well, it's because of genes. And it's like, why are all these genes mutating? Well, it's like they're evolving as a reaction to chronic cell damage. So therefore, they're sort of going backwards in evolution towards a single cell.
What you're saying there is the paradigms before make sense. They just aren't sophisticated enough to have all the nuances like you just explained, which is fascinating. In knowing now what you just explained, it makes a lot of sense. But of course, it's only because we're, looking backwards now. I can see why it took a while to get there.
Yeah, exactly. It's not that people were stupid or anything. It's just you're basically going one level deeper into why, right? So you've got, hey, cells are growing. Then you say, why are cells growing? Then you say genetic mutations. Then you have to say, why are genes mutating? It's an evolutionary process against chronic inflammatory damage. So therefore, that's where it is. And now, you're not going to stop a lot of these things in terms of chronic inflammation. So ulcerative colitis or something, like, yeah, you'd love to get rid of ulcerative colitis, or if you can identify it like tobacco smoke, then you can get rid of it, or asbestos, then you can get rid of it, right? But the other thing that's important is that certain things, now you say, okay, cancer is not a genetic problem. It's a problem that they've evolved or sort of gone backwards in evolution to these more primitive, right? So it's not a forward evolution, it's a backward evolution into a more primitive form. What's interesting, of course, is that that's the way pathologists have been describing cancer for 100 years. If you look at the pathological descriptions of cancer cells, they're called primitive, right? Anaplasia, which means going backwards in time, right? All of these terms tell you that they're not getting more sophisticated cells. They're going into a more primitive state, a survivalist state, a single-celled state, right? So that's exactly the way we've described them. But then now you have to try and figure out ways to deal with them, right? And that's the sort of challenge of the next sort of like 20 years. But that's where we are, and it's a really interesting story because, again, a lot of people just think it's all about genetics, but it's actually a lot more complicated than that. So, for example, if you have growth factors, well, growth factors are going to promote growth. So one of the things, for example, is obesity. If you have an excess of insulin, insulin is a growth factor. So therefore, that's going to play a role in cancer. And that's exactly what we found. So since the mid 2000s, say, what we've started to realize is that obesity is actually a huge risk factor for certain types of cancer. In fact, the World Health Organization identifies 13 different types of cancer as obesity-associated cancers. So again, that's, obesity doesn't cause genetic disease. It doesn't cause gene mutations, right? You've moved already way past the genetic paradigm. Because if you're calling this an obesity-associated disease, in the past, you'd have to say, so how does obesity cause gene mutations? And the answer is that it doesn't. Obviously not, right? But what it does is it is an excess of growth factors like insulin that are going to help the growth of these cancers that are developing. Since cancers are developing in all of us, we police them. But so there's always cancers developing, but we have very, very strong anti-cancer forces. So there's always criminals, but there's policemen. That's essentially it, right? So usually the policemen are like this, and it just squashes the criminals. That's the same thing. So normally we have cancer, but we have lots of strong anti-cancer forces, and they just squash them. If you give immune suppressants like prednisone or suppress the immune system for any of these autoimmune diseases, what happens is it goes like this, and then the cancers are okay. With age, same thing. Everything goes down with age. So immune system goes down with age, which allows the criminals to do this. So the other thing is, of course, that if you have obesity, you're going to have growth factors that's going to help the growth of these things, right? So it's all a balance between sort of the cancer, which is there in everybody, right? That's a totally different thinking. It's present in all of our cells. It's actually this balance between pro-cancer and anti-cancer. Normally, anti-cancer is like this, right? So that's where we think. So then we say, okay, well, immune system is there to sort of squash this, right? So what can we do? Well, that's the whole idea of immune therapy now. That's the sort of next big wave. It's already here, of course, if you look at the way that we treat cancer. It's a big thing. So one of the ways is that, okay, again, you think about criminals and policemen. Well, these criminals were hiding. That's why they were able to survive, right? Because the policemen couldn't find them. And one of the ways that the immune system, that the new immune drugs is to open up and expose them so that the policemen could find them. So that's exactly how some of these immune therapies work. They sort of break apart the sort of cloaking shield that these cancers had, and all of a sudden the immune system can see them, and it goes in and squashes the cancer before it gets to be a problem. Again, it's a totally different paradigm now. What we're trying to do is we're not trying to fix genetic problems, right? So cancer paradigm one, growth paradigm is kill. Cells are growing, kill them. Genetic paradigm is cells are mutating, let's find genetic cures. Now we're like into this sort of evolutionary paradigm, which is like, well, cancers are like an invasive species. Let's kill them with our immune system. Let's boost our immune system. Let's figure out ways that we can weaken them, right? A totally different way of thinking and a totally different paradigm that most people haven't recognized that we're in. Even oncologists, like even a lot of cancer specialists, they spend so much time thinking about treatments that they don't think about the sort of very interesting backstory of what is cancer, right? What is this thing? It's more like an invasive species than it is a genetic mutation problem. It doesn't change therapy so much, but it's an interesting way of thinking. So it shows you that there's multiple ways of attacking it. So whether it's immune therapy or boosting the immune system or trying to get rid of these growth factors like obesity.
When it comes to immune therapy, you talked about how, this is where we're at now as a modality that's being used. How many different cancers can they use that for? Where is that along the timeline of its, usefulness?
I think we're just at the beginning, really, because the whole evolutionary paradigm, really only developed in the last, say, 8 or 9 years, right? So it's relatively recent, only since the mid 2010s. So we've gotten a couple of good drugs, but now they're trying to develop. Now every sort of drug company is going down this path. So we're going to start seeing a lot more sort of exciting stuff. So what they're doing is they're doing all these, such sophisticated technology like CAR T, where they're taking your own immune cells, changing them up so that they recognize the cancer that you have. So if you have colorectal cancer, or prostate, they did it in prostate cancer actually. So they'll take your own immune cells, they'll say, oh, we need to make them do this, and then send them back in like a smart bomb sort of thing, and whack out just that thing that it's been targeted to. That's really, really impressive. Like the technology may not be there right now and it is very expensive, but that's the stuff they're talking about doing now, which is incredibly interesting, right? A lot of the a lot of these immune system treatments are sort of just beginning. We're just beginning to see. So I'm sort of optimistic that we'll start to see a lot more of this. But it opens up all sorts of different avenues when you see it as a sort of evolutionary, sort of an invasive species type of a problem. It opens up all different avenues for you for research, right? Because it's not just the immune system that you can target. You can target the growth factors, for example. So that breast cancer really loves insulin. So if you reduce insulin, then you can get rid of it. It also says that, hey, if you have a little bit of cancer, you don't have to get rid of all of cancer. because your body, like, you have, the cancer, you have the anti-cancer. A lot of times, if you find a cancer, it doesn't mean you need to cut it out, because your cancer things are so strong. And if you take it away, it'll eventually come back anyway, like this low level. So this idea of screening, and there's a lot of controversy in this, actually. So screening came out of this sort of genetic paradigm that if you could find a cancer at its very earliest stages, then you'll get rid of it and then you won't have to worry about it again. That doesn't happen. That doesn't work if you think of it as an invasive species. It's just like saying, if we find a bacteria in you, I'm going to give you heavy duty antibiotics and wipe out everything. It's not going to make you healthier. In fact, they'll make you quite a bit sicker in the long run, because those bacteria will just come back eventually and they'll be worse the second time and third time and fourth time, right? So at no point do we ever say to somebody, we need to get rid of every single bacteria in the body, because there's good bacteria, there's bad bacteria, and they get along fine. It's just like that, that whole movement before COVID anyway, let them eat dirt, right? Which is that idea that too much cleanliness is not that good a thing. You're actually not exposing yourself. Same thing with the peanut allergies, right? With the peanut allergies, the initial thought was, let's get rid of every single peanut we can find on this planet, and then there'll be no peanut allergies, right? Didn't work. It actually made the peanut allergy worse, which is a different story. But because people were never exposed to it, when they were, it was life-threatening exposure, as opposed to people who always had low-level exposures, like, people in Thailand, for example, who eat a lot of peanuts. They don't have very many peanut allergies because most people are exposed to it at a low level. When they get exposed to it, they get a little sick, as opposed to, a little sick all the time, as opposed to one time you see it and you're just really, really sick and could die. So it's the same thing. It opens up all these new ideas, because if you get rid of every single cancer that you can find, well, you're just going to be whacking out pieces of yourself all over the place, right? So it's not going to do you any good. So screening comes out of that. So if you find a very, very early cancer, you don't necessarily have to hit it with the hardest thing. They did this in South Korea, for example, where they did screening for thyroid cancer. So they ultrasounded people's thyroid, and if they found the thyroid cancer, they'd take it out. The problem is, almost all of those thyroid cancers were never going to be a problem, because your own anti-cancer forces would have kept it in check. So you actually derive no benefit whatsoever. So as people, they whacked out all these thyroids in people, the incidence of thyroid cancer skyrocketed, because they're finding so many more that they never found before. So it went up 10 times, but the mortality, the number of people dying of thyroid cancer, was unchanged, because those were thyroid cancers you didn't actually have to worry about. So this idea is that if you're finding super early cancers that would never have been a problem, and this is the controversial part, right? You see this in prostate cancer and you see this in breast cancer. So this is screening with PSA and screening with mammography. And if you do, let's take mammography as an example. If you do very early mammography, you're going to find a lot of cancers that never needed to be treated. You're going to you're going to take out a lot of breasts, and you're going to do a lot of radiation in a lot of people who won't benefit ultimately from that. So in fact, the data for screening from mammography is so controversial that they've actually gone backwards. They had originally pushed the sort of said, oh, you should do mammography at age 40, and then now they've pushed it back out in some cases to 50. Now there's a lot of controversy on, some people think it's a good thing, some people think it's a bad thing, but it comes out of this idea that finding it too early is not necessarily something that you have to deal with, because we can deal with it ourselves. It's more of that. Yes, it's like finding a bacteria on your skin. Yes, there's bacteria on your skin, but so what, right? It's going to be fine. It's never going to be a problem. So don't cut that out. So it's just an interesting way of looking at it, that all these things start to make more sense. Because if you took the genetic paradigm, it would have said that, hey, if you find a very early cancer, you should take care of it right away, immediately, because it will become a worse cancer. That's not necessarily the case.
And coming back to your thyroid example there, you didn't talk about this aspect as well. There's so many different layers to this. The fact that if you're taking a thyroid out, that has, profound functions in the body for it to be healthy. And you're now removing that, so the body's not going to be as healthy as it was before.
Absolutely.
Plus the
And
stress layer, you're going to stress that person out. That's going to raise cortisol in the system. And then that's causing a whole influx of stress response chronically for that person.
exactly. And this is the controversy, because it's not like the treatments have no side effects, right? So if you do uh, lumpectomies, and if you do a lot of lumpectomies and radiation for early breast cancer, you're going to get side effects because you're doing so many of these, right? There's surgical side effects, there's radiation side effects. So your benefits must outweigh those risks. So at some point, right, and everything in medicine is sort of risk versus benefit. At some point, the risk of that early stage cancer in a normal person is so low that the risk of treatment is much higher than the risk of the cancer itself, right? And that's the same problem you see with antibiotics, and that's why people say we're giving too many antibiotics, because it's so easy to give antibiotics that you're giving it for situations where there's almost no benefit to the antibiotic, but now you're getting the risk of and there's no benefit, but the risk is starting, because the benefit's so low, the risk is actually higher than the benefit. Same thing with these treatments. So people have been talking about not doing PSA screening, about pushing up the age of mammography. There's controversy about chest X-ray screenings, and you can start to understand the sort of underpinnings if you look at it from the evolutionary standpoint as opposed to the genetic standpoint, because screening everybody with a CT every year from age 10 sort of makes sense from a genetic standpoint. It doesn't make any sense from the evolutionary paradigm.
You make such a good point, and I wanted to go there as well. The fact that these treatments could, contribute to cancer, the modalities being used, or the screening methods. Which brings me to something you talk about in your book, which is fascinating. The fact that cancer drugs actually cause cancer.
Yeah, and that's the interesting thing, because the original cancer drugs, remember, are based on killing cells, right? So the chemotherapies, the surgeries, you're trying to cut it out, you're trying to burn it with radiation, or you're trying to poison it. So that's damage to the cells. Well, if you think about the evolutionary paradigm says when you're damaging cells, cells are going to evolve to a more survivalist state, or move towards that single-celled state that we all had, right, in response to cell damage. So you've got all these treatments that are damaging cells because we've designed them to damage cells. So the very treatments from sort of the paradigm one, the very treatments that we use to cure cancer also cause cancer, right? And you can't understand that until you get to the evolutionary paradigm, which is fascinating, because if you think about chemotherapy, we've all known this. We've known this for 30 years. If you treat somebody with chemotherapy like cyclophosphamide, you get what's called secondary malignancies. That is, you treat somebody for lymphoma, 20 years later, the risk of, you know, bladder cancer will go up, or something like that, right? You treat somebody with radiation, their risk of cancer goes up. You radiate somebody, you give chronic, surgery, you can get, damage at the surgical site. You can get cancers at the surgical site. So all of those treatments that we use to kill cells and to treat cancer also cause cancer. And that's the reason why.
Well, now that we understand this new evolutionary paradigm, it gets me thinking about, cancer science as a whole, where doctors and scientists are with this whole thing. To be honest, you're the only person I'm hearing talk about this new paradigm. So what I'm getting at here is, for us to move forward with ways of preventing and treating cancer, and just furthering the science, we all need to be on the same page with this new paradigm. Are we getting there? Where are we at with that?
Yeah, it's very slow. And that was the reason I was so interested in this paradigm, is because as I was reading about it, and I sort of stumbled into it from the obesity side of things, so I was trying to see, why is obesity associated with cancer? And that was a really interesting question to me, because it didn't make any sense, because remember, I was raised on the genetic paradigm. That's where my medical school training was, and so on. So the whole thing is that I was reading this, I realized that, hey, the science had moved way past this genetic paradigm into this evolutionary model, but nobody was talking about it. And I think that what happens is that there's so much money that was pushed into this genetic paradigm. Nobody wants to admit, hey, that's not quite correct. We've moved past that. It wasn't wrong, but it wasn't right either. And we need to push past that. So, in fact, when you go to, and given talks to like oncologists and stuff, and they don't know anything about it because nobody wants to talk about it. They just want to talk about drugs for treatment. They don't want to think about what causes cancer in the first place, which I think is the most fascinating topic of all. I think it's the most fascinating of all the topics, actually. And it will feed back into why obesity is a risk factor. In fact, one of the biggest risk factors for cancer, which is strange because if you look even back at the 80s, so the whole obesity diet connection to cancer is hugely problematic for the genetic paradigm, because if you eat a bad diet, it doesn't mutate any genes. So if you're saying that it's all due to gene mutation, then diet should play zero role, right? Because diets don't mutate genes. It's not mutagenic. So it's hugely problematic. But if you look back at studies from the 1980s, they went back and they said, let's look at what causes cancer. How much can we attribute to each thing? So the biggest risk factor for cancer was smoking, by far. It's like 35% of cancer could be attributed to smoking. There was a whole bunch of small stuff. So there was, radiation and drugs and all that. That's like 2%, 2%. And then there's another huge, huge risk factor, which was about 30% of attributable risk. And that was diet. And nobody wanted to go there. It was like, whoa, okay. We took care of the smoking part. We've had education. We tell people don't smoke. We tell people smoking causes cancer. Like, how many people don't know that? Like, zero people who smoke don't know that it causes cancer. They just don't care, right? But there's this huge other bucket that's almost as big of attributable risk. And these studies have been replicated over and over and over for the last 30 years of attributable risk. And diet and obesity is that second huge bucket, and nobody's talking about it. Why? Because we're all stuck in that genetic paradigm of what causes gene mutations, because smoking fits so perfectly into that sort of paradigm. And radiation and some of these other things, right? Radiation exposure and some of the, it's asbestos exposure and wood dust and all this other stuff. Those are all small, but we're ignoring that giant bucket of dietary obesity because it didn't fit. So nobody talks about it, right? And it's probably due to the growth promoting effects of some of these hormones, which tend to favor, the cancer, right? It's all the balance of cancer versus anti-cancer. And if you have a lot of insulin, a lot of growth factors, which comes from your diet, you're pushing up this one, right? And this one stays the same. That's why your risk of cancer goes up, obesity-associated cancers. And obesity-associated cancers are not just a little bit. It's like two of the biggest ones are breast cancer and colorectal cancer, which is sort of the number 2 and 3 cancers in the world, right behind smoking.
We keep touching on this insulin piece related to cancer and the growth hormone impacting it, and I want to get there. But before we do, when you talk about food not affecting the genetics, what pops up for me is thinking about our food system these days and the fact that we're putting chemicals on a lot of that conventional food, spraying with pesticides, herbicides, and then processed foods, quote unquote foods, because, arguably we could call those something totally different. They don't even fit under the real food category. I would argue that. So, what I'm curious is your thoughts on those two categories specifically. When pesticides, herbicides are coming into the body and processed foods, could those specifically impact the genetics?
It's possible. It's possible. And certainly there's a lot of people concerned about it. That's why people like to do the organic farming and all that sort of thing. But again, the risk is hard to quantify because it's probably relatively small compared to, say, obesity. Now, some people argue that, hey, it's all these chemicals that are causing the obesity, right? But that's, a bit, I'm not sure about that either. So again, if you look at the risk of those chemicals that we use in farming and all that sort of thing, and look at attributable risk, it's probably like 1 or 2% versus obesity, which is like 30%. So yes, I think that there is a role for them. And a lot of them, of course, are classified as carcinogens. So the World Health Organization maintains a huge list of carcinogens, class 1, class 2, class 3 are carcinogens. There's like 200 plus compounds on there. And a lot of them are stuff we use all the time, right? Of the ones classified as a carcinogen, the herbicides and the pesticides are probably higher up than most. But it's never been shown in a good study that organic food reduces your risk. Because again, if sort of like, if the attributable risk is only 1 or 2%, most of us are not getting exposed to that much of the same chemical all the time. But it probably plays a role. It just hasn't been proven yet. Like, organic food, people would love to show that eating organic food causes less cancer, but I haven't seen any study that's convincing that is true.
It'd be interesting though if they did study that. And another thing that popped up as you're talking about that is genetically modified foods, because there we're directly influencing the genetics of what's going into our body and interacting with our own cells. And then again, this goes more to paradigm 2 with the genetics. And when that interaction takes place, is that affecting things related to cancer, changing the genetics? I'm assuming there's not been research done on that, but maybe you know
Yeah,
better.
again, it sort of makes sense that these genetically modified foods um, would be a problem, but again, they have to really. It's more than that. It's more they have to be causing damage to cells in order for it to be a problem, and I think they can, but it's hard to know. A lot of the foods these days are genetically modified, but even if you look at the human sort of what we eat, it's been modified significantly over time anyway. It just wasn't done with these sort of tools. What they did was they breed this together with this. So you look at wheat, for example. Wheat is, if you look at the ancient wheat in ancient Egypt, it's quite different than the wheat we eat today. It actually underwent a huge change in the 1960s during the so-called Green Revolution, where people developed this dwarf and semi-dwarf wheat, and it so wheat has a long stalk and a little bit at the top where you can get the flour from. All that stock is useless. And so what they did was they wanted more stuff at the top. If you made more stuff at the top and the stock was long, it just flop over and then rot. So what they did was they developed things so that the top was huge, and then they had to shrink the stalk so that it wouldn't flop over. So this is called dwarf and semi-dwarf wheat. So it went from, and that was developed in the 60s. And that was the Green Revolution, because at the time we were worried that there's too many people on Earth and we'd all die of starvation. So we didn't all die of starvation because crop yields just went up astronomically. And it was in part due to the changing of the wheat from sort of original wheat to this dwarf and semi-dwarf wheat, which has now replaced like 99% of the wheat that we grow, right? So compared to 100 years ago, it's totally different. So that's a genetic modification. It was just done through selective breeding as opposed to the tools that we use today. So, even back in the 60s, 70s, 80s, we're already eating foods that are quite different. I mean, you look at the supermarket, like the number of varieties of fruits that we have, for example, is just much higher than it used to be. It's not the same. You get pink pineapples, and you've got, the white peaches instead of the regular peaches, right? So there's all these varieties that have been developed through selective breeding, which actually is a change in the genetics. So whether doing it artificially through genetic modifications, like we do with sort of specific targets, it's a good question whether or not that's more dangerous than what we're eating now, because what we're eating now is also modified.
I hear what you're saying, but I feel like there is that step up when you're going in there and
Yeah,
modifying the genes, a human doing that in a lab versus
yeah,
picking what's breeding together.
exactly. I think you're right too. I think it sounds a lot more iffy. There sounds like the potential for more harm in that situation, but it's not been proven that that's the case. I mean, most people still try to avoid GMOs when you can. And most people try to eat organic if they can as well, but for the same reason, we all have those sort of concerns about it. It's just not proven.
I think the big thing to keep in mind here is what you talked about earlier, where we're all going to have cancers through different parts of our lives. And what we want to do is try and control what we can to keep the immune system strong so it can kill those cancers as they develop, and hopefully they won't turn into anything major.
Exactly, and I think that's the hope. And again, the whole point is that you have to go where the risks are, right? If your risk is only, attributable risk is only 1%, and you are able to get that down and have that risk, that's amazing. But that's only 0.5%, as opposed to diet, which is, if that bucket is 30% and you have it, it's a 15% benefit, right? So it's a huge sort of issue. And I think that one of the things is making sure that we're looking at all these things properly, because people have this idea that it's all about screening and stuff, but it's not. You can do so much more to protect yourself against cancer other than just screening.
Well, let's talk. We keep alluding to it and touching on it, but let's get deep into the insulin piece. So, this is obviously something that we all have control over or relative. And let's get into the physiology. So, when it comes to insulin and spiking that and its relationship to cancer, what's happening there?
Yeah, so again, it's a matter of sort of growth factors. So anything so remember, if you're an adult, you generally don't want to grow, right? You don't want your liver to grow, you don't want your kidneys to grow. You don't Growth is bad. When you're a kid, of course, growth is good. You have to go from a baby to an adult, but when you're an adult, stuff is not supposed to grow. So growth is bad. So if you have factors that increase growth, then it's generally bad, because if you have a cancer that's brewing in there, for example, it's going to be highly dependent on growth. So insulin is a growth factor. Insulin's also a nutrient sensor. So when you eat, insulin goes up. So what you eat plays a big role in what your insulin levels actually are. It turns out that insulin, and for years that's all we thought insulin was, but insulin turns out to be one of the most sort of fundamental growth factors we have. In fact, if you look back at primitive animals, insulin was not used as a nutrient sensor before, it was used as a growth factor. As we evolved, we actually use the same factor for both growth and nutrient sensing. And that makes sense, because insulin tells you that nutrients are available. So you only want to grow when nutrients are available, right? Because if you grow in a period of famine, well, you're huge, you need a lot of food, and there's no food to eat, that's not going to be good. So in order to survive, our body decided, hey, we're going to use the same molecule, insulin, for both to sense that nutrients are available and to signal the body to grow. So therefore, we're going to be able to link what's on the outside, the nutrition, and what's on the inside, which is the growth. And the whole thing is that if you increase insulin, like with obesity, if you're eating foods that spike insulin, if you're eating all the time, obesity and type 2 diabetes are both states of high insulin. So if you have high insulin, not only do you have obesity and type 2 diabetes, but you are also signaling your cells to grow quickly. Cancer cells actually are many of them are very insulin dependent. That is, in order to grow, they need glucose. They live on glucose. That's what fuels their growth more than anything else. In order to get glucose from the blood into the cell, they need insulin. So they love insulin because they're trying to grow, grow, grow. Remember, the cancer cell is like a single cell. It wants to grow as much as possible at the expense of its neighbors. In order to grow, it wants as much glucose as possible, so it puts out as many insulin receptors as possible, so it's much more insulin sensitive than the cells around it, so that when insulin is available, it'll pull that insulin and grab that glucose. So if you look at a breast cancer, for example, breast cells have very few insulin receptors. They don't need it. But breast cancer cells have tons of insulin. In fact, in the lab, if you deprive breast cancer cells of insulin, they shrivel up and die. They can't survive without the insulin. It's a growth factor to them, right? If you take away the growth factor, they don't grow. So, for breast cancer, for colorectal cancer, these are both very insulin dependent for their growth. So therefore, if you're providing a state of high insulin, you're going to tip the favor towards cancer growth. There's a group of people in Ecuador who have this funny genetic mutation called Lauren dwarfism. And they don't sense insulin at all. And the funny part about it, so they basically don't have any insulin, they don't have the growth factors that come with insulin, so they're all dwarfs. They're short, but they also don't get cancer. It turns out they're almost completely immune to cancer. That's crazy. So it's like if you completely stop that insulin sensing, then you completely got rid of that cancer. So that's just one of the things that's important. And the reason that's important is because we can control the insulin levels by what we eat. We can eat things that are not going to spike insulin. We're going to eat sort of other things that are not going to spike growth. We can do things like intermittent fasting, which is going to allow your insulin levels to fall, because remember, insulin is a nutrient sensor. So there are things that you can do that may impact your risk. And mostly it comes down, those things will also affect your weight, of course. So therefore, you can get a good proxy of how it's doing by your weight.
So when it comes to cancer and insulin, is it all about prevention, or for somebody that has cancer, it sounds like it's both. Is it for prevention and for somebody treating?
It's going to be mostly for prevention. On the other hand, if you have cancer, then again, you don't have to get rid of all of the cancer, but you can sort of deprive cancer of much of its growth potential by, trying to limit insulin as much as you can, right? Again, if you have an obesity associated cancer, you get rid of the obesity, hopefully it'll be better. So if you have an early stage colorectal cancer or early stage breast cancer, it doesn't change what you should do. You should still do everything that the standard oncologist will tell you, whether you need surgery, whether you need radiation, whether you need chemo. It doesn't change any of that. But as an adjunctive therapy to keep yourselves well, because remember this, you could have any of those cancers and still live another 20 years. You just don't want that cancer to come back, right? You have a tendency towards that cancer. So if you know that insulin is a huge risk factor for breast cancer, you should try to limit insulin. Or if you know that it could have colorectal cancer, you want to try to eat as well as you can to prevent that. So it's mostly prevention, but in terms of treatment, people have tried to use it, with variable results, because by the time you get to that stage, those sort of things, it's sort of like if you think about lung cancer, you say stop smoking. Well, that's really important, but it's not going to do anything for your lung cancer, right? You can stop smoking the minute you get that diagnosis. You still need all the usual treatments, the surgery, the radiation, and all that. Yet at the same time, smoking was this sort of overriding risk factor.
You mentioned fasting there, and where that really does fit into the treatment part when it comes to conventional treatment is stacking that on to chemotherapy. So, can you talk about how using those two together can be powerful?
Yeah, it's being studied. So people are trying to combine the fasting with the chemotherapy, and it's for a different reason. So a lot of chemotherapies target the fast growing cells. So that's what they do. Cancer cells are growing quickly. So chemotherapy drugs they kill fast growing cells. It also kills your own body's fast growing cells. That's why your hair falls out, your lining of your intestines gets damaged, you get nausea, you get vomiting with chemotherapy. Because they're killing fast growing cells. So with chemotherapy, the idea is kill fast growing cells. With fasting, what you're trying to do is put your own cells into a more quiescent state. So when you fast, your own body cells slow down their growth. So but the cancer cells don't, because they're just sort of growing. So then when you give the chemotherapy, your own cells are going to take less of the hammering, and more of that chemotherapy is going to go into damaging the cancer cells. So what people do is they try to fast for like 24 hours before and after chemotherapy, for example, trying to give that chemotherapy a little bit of a better edge and protecting yourself against some of the bad side effects of chemotherapy. So that's one way people have used the fasting for that. So it's a different reason entirely, and it perhaps doesn't work for some chemotherapies because they don't have that same target. But it's an interesting application of fasting.
Coming back to the obesity, type 2 diabetics, insulin, which, somebody who's overweight or obese is going to have insulin resistance. And that is basically a synonym for having too much insulin in the body, hyperinsulinemia. So, what I'm getting at here is they also have this other factor if they're type 2 diabetic and injecting insulin, where they're now throwing more wood on the fire. So basically, they're going to make themselves gain more weight because they're taking in more insulin, which is a growth factor. Plus, it's going to it's going to be a growth factor for cancer as well. So you can just see how
Yeah.
all this ties together. And for somebody in that state where they're overweight, obese, type 2 diabetic, injecting insulin, like everything's just cycling against them at that point.
Yeah, exactly. And the idea that you should treat type 2 diabetes with insulin, um, it had its heyday sort of in the 90s, 2000s. People thought, hey, just give more insulin to get those blood sugars down, and then you'll do better. That idea has sort of gone away. There was a couple of large studies in 2008 that really sort of put a hole in this idea that giving insulin was like great medicine. So, and the risk of cancer was always a concern in that case. But again, there's a lot of other issues there. The weight gain, of course, was the most visible problem of that, right? And that whole thing, I mean, I talked about it in the diabetes code as well, is in type 2 diabetes, you have too much insulin. Insulin levels are too high, so why would you give more? It doesn't make any sense at all. It's actually the wrong thing. And people knew it because you take insulin, you gain weight. As you gain weight, your type 2 diabetes got worse. As your type 2 diabetes got worse, you had to take more insulin, which made you gain more weight. You can see how that's not going to end well.
So for somebody that is in that boat, what do you recommend to them?
I think that the best thing is really to um, sort of focus on the diet. So, in terms of diet, there's some general principles that are pretty well accepted. One, try to eat natural foods, right? Don't try to eat a lot of processed foods. Try and cut down the sugar. And then to me, it's also don't eat all the time, right? In other words, make sure you have an adequate period of fasting in between, because it's a balance between insulin, nutrition, being good, and then letting your body use that. But yeah, I mean, from a cancer standpoint, it's a lot harder to measure. Like even these things about insulin causing cancer growth, there's a theoretical risk, but because the risk is spread over like 20 years, and even if you gave somebody a lot of insulin, like these type 1 diabetics who would get it at age 10 sort of thing, it's hard to show because they don't get cancer until they're sort of like 60, right? So studies generally are not in the long term. Nobody studies people over that length of time because it's just insanely expensive to follow people for 40 years. But it's a factor. Like it's a huge factor.
And in the research, have they found any cancers that are immune to this insulin response?
Not all cancers show that risk. So it's mostly the obesity associated cancers. Like lung cancer, insulin plays very, very little role in lung cancer, whereas breast cancer and colorectal cancer plays a big role. And other ones are moderate. So pancreatic cancer, it plays a big role. The interesting part about the obesity associated cancers is that they've become a bigger and bigger problem in the last 20 years. So, whereas the number one cancer in the world has always been lung cancer, it's becoming relatively less important because smoking rates are going down. We're actually starting to see a lot of non-smoking associated lung cancer, and nobody knows why that is, but it's definitely a thing. We're starting to see this all the time now, which is super strange. So there's more to this story, but the rates of obesity associated cancers are going up and up and up. The only one of the obesity associated cancers that where mortality has gone down is colorectal, and a lot of people think that's because of the catching it earlier, like the screening colonoscopy, which again, they've recently pushed it back earlier. So instead of age 50, they've actually started to push it to 45 because we're seeing earlier and more aggressive cancers. And the thing is that cancer is an extremely complex topic. So it's not just one thing generally that affects it. So yes, genetics can play a big role, but so can other things, right? So you don't have to be overweight or obese to have breast or colorectal cancer. Many, many, many people get it who don't have that risk factor. It's a risk factor. It's a number of things that altogether create your risk. And it's the same for anything. It's like heart disease. The risk of heart disease is not related to one thing. It's related to age, it's related to sex, it's related to family history, it's related to smoking, it's related to weight, it's related to physical activity, it's related to stress, right? There's like 10 things that are risk factors for cardiovascular disease. It's going to be the same for that, right? So whereas it's important to focus on these, it's not the only thing. So, the last thing I want to see is sort of people saying, "Oh, you have breast cancer. You didn't eat right." And that's not the case. Same thing with lung cancer. Now we're starting to see a lot of lung cancer that's not smoking associated. So this sort of blame game, which I see a lot of sometimes, is on social media. It's quite destructive, right? It's not, as a physician, that's not what you ever want to be doing, right? You just want to treat people, make them better. You don't need to blame people for stuff.
Well, we've gone over a lot of the risk factors when it comes to cancer. We've talked about obesity, type 2 diabetic, and the insulin response facilitating growth, and potentially things like GMO foods and organic foods,
Yeah.
how that could be tied into this. Smoking, obviously. But I want to make sure that we cover all, at least, of the big risk factors when it comes to cancer. So, what are the other ones that we haven't gone over?
Those are the big runs, but those are the modifiable runs, right? Because there's a lot that are genetic. Genetics does play a huge role in it, right? Obviously, if you have a family history of breast cancer, then your risk is just much higher. So it's not that it's not important, it's just that it's not a modifiable risk factor. You can't change your genes. Same thing with age and sex and stuff, right? Everyone gets older, and that's not a modifiable risk factor. But those are very important risk factors. Where genetics plays a big role in is screening, because of course, if your risk goes way up, so if you have a family history of colorectal cancer, then your recommendation is to start colonoscopy screening earlier. Same with if you have a family history of breast cancer, then you need to screen earlier. So it doesn't make sense to screen everybody in the world earlier with colonoscopy, like age 40 is what it is now. But if you have a family history of colorectal cancer, then you screen earlier because you might have problems earlier. So genetics, is still it still plays a big role in a lot of things. So, and it does affect things like screening. It's just that um, you can't change your behavior the same way you can with smoking, the same way you can with diet. Exposure to asbestos, exposure to wood dust, exposure to these sort of things, smoke.
What about specific foods? In the book, you talk about green tea having this anti-cancer effect, and I'm curious if there's any others people can use preventatively to help, again, stack the favor in their hand in a better way.
Yeah, people have always looked for it, and the term was chemoprevention, and the idea was, is there something that can prevent cancer? There hasn't been a lot, actually. So green tea does have certain compounds. Most of the research was done in Japan, where they drink a lot of green tea, and that's basically what that's basically the one compound where there was probably the most evidence, although it's still very sparse. The thing about green tea is that it has certain compounds that people say have been associated with less cancer. When you think about it, the risk reward ratio is skewed in terms of benefit because the risk of drinking green tea is almost zero. It's pretty well zero. So if you drink more green tea, you're probably going to do a couple of things. One is you're going to be drinking less of the other stuff, which is fine if it's water, but not so fine if it's like soda or something, right? So, and then perhaps you might get a benefit of the green tea itself. But again, it's when you look at all the compounds, there's a lot of expensive stuff that people try to sell you to prevent cancer or keep cancer away. Most of that has less data than green tea, which is, you could buy a box at Costco, 100, tea bags for like $10 or something like that, right? As opposed to some of the more expensive stuff, which actually has a lot less data behind it. So the green tea is just interesting. One, because it's probably one of the better studied compounds. Two, it's widely available and it's cheap. And three, it basically has no risk, as opposed to going out and buying, a bottle of this really expensive thing that they tell you will prevent cancer and cost you like $100, and you actually have no idea what's in it, right? At least when you go to wherever your grocery store and get green tea, you're almost certainly going to get green tea.
And Jason, I know we're coming up on time here, but we'll end with this. Somebody tuning in right now who is recently diagnosed with cancer, and this is a big question, I know, and it's got a lot of nuance to it, but in a general sense, what would you say to them as somebody that studied this and knows this new paradigm inside out and a lot of the nuances to prevention and treatment? What would you say to that person?
I think if you have cancer, it doesn't really change the treatments because the treatments are well studied. So you should still do everything that you're supposed to be doing. It doesn't mean like you go against, saying, I'm not going to do this thing that my oncologist tell me. No, you probably should do all of that. But you should also look at boosting it where you can with things that are relatively sort of high benefit, low risk. So eating, getting to a proper weight, for example, the risk of that is very low, right? And doing that by eating unprocessed foods, there's almost no risk in that. Intermittent fasting, very little risk in that. But the benefits are potentially there. There's also a lot of other, these sort of adjunctive things. Adjunctive just means add in addition to the other stuff, the chemo, the radiation, the drug treatments, and whether that's and some of this is not well studied, but again, it doesn't matter if it works or not. If there's no risk, then why not do it, right? And that's things like the fasting in conjunction with chemotherapy. What's the risk of that? If your weight is very, very low, then perhaps no. But if your weight is normal or high, then there's no very little risk to doing some fasting, and perhaps it boosts the effect of the chemotherapy. It's not strong data there, but then again, it's not a matter of if it's proven to work. It's a matter of what's the potential risk and what's your potential benefit. And if your potential risk is very low, then you should probably just go ahead and do it. There's all kinds of other things there, things like green tea. Well, the risk is just very low. So why wouldn't you? Why wouldn't you try and push up your consumption of green tea if that's what's worrying you? Your risk, almost zero, right? Some of these other compounds that people will sell you, perhaps not. But that's the thing, is to try and take these things which are sort of don't have a lot of risk associated with it, that might have some potential benefit, and then take it to, and they're not all easy, like getting to a normal weight, getting rid of your type 2 diabetes. That's not easy stuff, right? It's a job in itself. So it's not that I'm saying, oh, drink more green tea. That might be part of it, but some of it may be a lot more difficult. Losing weight's not easy. Getting off of insulin by reversing type 2 diabetes, that's not easy. So some of that is a lot of work, but could have potential huge benefits, not just for the cancer, but for your overall health.
Yeah, and where that really comes into play too with the weight loss piece is people that don't have cancer yet and want to prevent. Because like you said, there's just so many health benefits. That to me is such a foundational piece of, being healthy to get your weight to a healthy level. So we'll end on that, Jason. Really appreciate you coming back on the show. We're going to link up your book, The Cancer Code. We're going to link up your social media, everything in the show notes. And always a pleasure. Thank you.
Thank you so much. All right, bye.
Now that you're done with Jason, you're going to want to stick around here and catch my chat with Fred, where he shares the story of how he healed from cancer. I'll see you over there.
So I'm in front of the doctor and he tells me, okay, I have bad news. It's a cancer. The more I looked into it, the more I realized that there is a huge gap between